experiment, we investigate acceleration using Newton's second law and compare theoretical predictions with experimental results obtained from a motion analysis. The system under study consists of a glider on an air track connected by a string to a hanging mass, which provides a constant pulling force. In this equation, g is the gravitational acceleration. This equation assumes ideal conditions where friction and air resistance are negligible. While in reality, these forces are never completely absent, in this setup, they are sufficiently small compared to the pulling force and can reasonably be considered negligible for calculation purposes. This simplification allows us to focus on the relationship between force, mass, and acceleration, without introducing unnecessary complexity. Experimentally, acceleration will be determined in three ways: from the slope of the velocity, time graph, from the analysis of position, time data, and from the mean value of the acceleration, time graph. Each method provides an opportunity to evaluate the accuracy and consistency of our measurements. The comparison between theoretical and experimental values will be quantified using percent error, highlighting potential sources of discrepancy such as measurement limitations, sensor resolution, and small unaccounted for forces. By the end of this lab, we aim to deepen our understanding of Newton's second law, the reliability of different experiment methods for determining acceleration, and critically evaluate the assumptions such as neglecting friction and air resistance. The underpin theoretical models. My name is Stephanie Howard, and that was the introduction to our lab.
Hello, my name's Conrad, and I'll be doing the materials. First off, we have the glider, which is the cart, which is the object that moves along the track, which is this item. Second off, we have the air track, which is this whole metal structure, which will minimize the friction during the glide's motion. Third item we have is a set of hanging masses, which is this thing where normally we'll have weights, but in this example I do not have weights here, which is this part. The string, which connects the glider to the hanging mass. The pulley, which is this wheel right here, which guides the string over the edge of the track. We have the balance right here to measure the mass of the glider and the hanging masses. We have the motion sensor, the capsule motion sensor, which is this right here, which can help to record the position, velocity, and acceleration data. And we have the computer with the passcode software for data collection and graphing analysis. Also, we do have the air pump, which allows us to pump air into the air track.
Hi, my name is Gregorio Livas.
And my name is Conrad Su, and we'll be doing the procedure.
So for the first step, we did the setup, which we placed an air track on a level surface and connected the glider to the hanging mass using a string that passes over the pulley. We positioned the motion sensor at one end of the track so that it can continuously detect the glider during its motion. Then, we confirmed that the motion sensor is aligned with the glider's path and is free from obstructions. Next, we measured the masses, which we used the balance to measure and record the mass of the glider, and measured and recorded the total mass of the hanging weights. Next, we calculated the theoretical acceleration using Newton's second law, which is acceleration is equal to the mass of the weights times gravity, which is 9.8, negative or positive, over the mass of the weights plus the mass of the glider. Next, we did the position versus time graph, which we started by using the capstone. We started using the capstone software and set the motion sensor to record position as a function of time. Then we released the glider from the rest and allow it to accurately accelerate. Then we release the glider from rest and allow it to accelerate under the pulling force of the hanging mass. Then we recorded the data from the motion sensor, ensuring the full motion is captured. Then we repeated it until a smooth position time curve is obtained.
Alright, for the next part, we have the velocity versus time graph, where we use the capstone software to create a velocity time graph by selecting velocity as the measured variable. We identified 2 points on the graph corresponding to the initial and final velocities, and we calculated the experimental acceleration as the slope of the velocity versus time graph. In the next part, we created another graph, which was the acceleration versus time graph in capstone. We highlighted the regions corresponding to the interval of motion and used the statistical tool to calculate the mean acceleration value. In the data analysis, we used the initial and final velocity values from the position time graph and calculated the first acceleration, which was labeled as acceleration 1. We compared the 3 experimental accelerations from position, velocity, and acceleration graphs with the theoretical acceleration, and we computed the percent error for each method. The percent error is equal to the theoretical value minus the experimental value divided by the theoretical value times 100. And in the final part, we will have the discussion and conclusion, where we will discuss possible sources of error, the effect of neglecting friction and air resistance, and which measurement method is most reliable. We will also be going over the group consensus on error thresholds and whether it was a good, regular, or bad experiment. Thank you.
Hello, my name is Jorge Valdez, and we're going to be going over our calculations for our Lab 3. So we started off by doing our theoretical acceleration, and this was the formula for it. We had to get the mass of the weight and then multiply it by gravity, and then have that over the mass of the weight plus the mass of the little scale thing that it was on. And then for our theoretical acceleration, we got it to come out to negative 0.91 meters per second squared. For our next step, we had to figure out what our initial velocities and final velocities were, and we had to use this graph to get the numbers for those velocities, or get it for the equations. So for position 1 and 2, it was between position 1 and 2 was, position 1 was x1, and then position 2 was x2, and we got negative 0.04 for position 1, and then negative 0.07 for position 2. Position 3 was x3, and then position 4 was x4, and then these were our positions and then our times. So we got our position changes by subtracting these two together, and then our time changes by subtracting these two together. And then for our velocities, we did position over time to get our initial velocity, and then we did the same thing over here for our final velocity. For acceleration 1, we started off calculating this from this equation right here, but we got messed up a little bit by our TA, because initially we did our final velocity minus our initial velocity over our time change for final minus our time change for the initial, and initially we got a negative 22 point something, and it was clearly incorrect. So we tried using the actual final time, which is time 4, 1.15 seconds, and then minus our actual initial time, which is 0.4 seconds. And we got a much more reasonable answer, which was negative 1.2 meters per second squared.
Hey, my name is Santiago Arras. I'll be explaining the second half of this lab report. So back where we're on step 3 now. And right here, to figure out our second acceleration, we went ahead and using capstone, we went ahead right here, and as you can see in this middle velocity chart, using our first 2 points and using the highlighted graph, that we got a mean of negative 0.31. And moving forward from here, we did the same thing on the last 2 points, which means we would get a mean of negative 0.91 using the last 2 points of the graph that we got. And so combining those two together, we got a velocity change of negative 0.56 right there. And then for the times, we just used the same times originally as we have gotten from the previous chart, graph right here. So combining those two, we got a difference of 0.4, giving us a total acceleration of negative 1.4 for our second acceleration using capstone itself. So after we came to this conclusion of this acceleration, we went ahead, and for acceleration 3, to be quite honest, we were a little confused as to how to come close to this, come to this acceleration that we concluded on. And we spoke to the TA, and from our understanding is that it was okay for us, as you can see here, to take the mean acceleration from the first 2 points and combine it with the mean acceleration from the last 2 points. So as you can see here, we got negative 1.36 on the first 2 points, and then on the second one, the capstone clearly tells us it's an mean acceleration of 2.95. So going from there, we combined them both, and we came to a conclusion for acceleration 3 of a negative 1.59. That's how we concluded our thing. Very simple. That's what we were told. And so moving on to the last step right here, we just gotta figure out our percentage errors using this calculation with our original theoretical value of negative 0.91, and using our experimental values that we got from acceleration 1, 2, and 3. So as you can see, we did the work here. So negative 0.91 minus negative 1.2, divide that by the same theoretical times 100. We got, for acceleration 1, we got a error change of error percentage of 31.9. And then for our second acceleration, same thing with our confirmed value for acceleration 2. We then got a confirmed value of error percentage change of 53.8 for acceleration 2. And for the last acceleration, same thing. We went ahead and we got the highest percentage error of 74.7. And so we went ahead, we did that, and this is our lab report right here. And yeah, that's about it.
Hi, this is Kason Kelly. In this lab, we apply Newton's second law to study acceleration using a glide, a set of hanging masses, and a capstone software for data collection. We determined acceleration in 3 different ways: from the position versus time graph, from the velocity versus time graph, and from the acceleration versus time graph. By comparing these results to the theoretical value of acceleration, we were able to evaluate the accuracy of our experimental methods. When analyzing the percent errors from each method, we found that they were not exactly the same, but they were relatively close. This is expected because each method is based on the same physical motion but uses different data processing and calculations. Small variations naturally arise due to the sensitivity of the motion sensor, how we scaled the graphs in Capstone, and the precision of our mass measurements. Friction along the track and slight irregularities in the weights also contributed to the discrepancies we observed. It is important to note that the percent error should not be expected to equal 0. Real-world experiments always include uncertainty, whether from environmental factors, equipment, or human handling. What matters is that the errors remain reasonably small, showing that the experiment successfully represented Newton's law. As a group, we decided that percent errors under 10% indicate a good experiment, errors between 10 and 20% are regular, and anything beyond that would suggest the need for adjustments or careful reevaluation. If given the choice to calculate acceleration again, I would use the velocity versus time graph. This method provides a straightforward linear relationship where the slope represents acceleration, making it less prone to compounding errors than the other approaches. Overall, this lab demonstrated both the strengths and limitations of experimental data. While theory provides an ideal prediction, experiments remind us of the influence of small but unavoidable errors. Understanding and managing these differences is a key part of mastering physics.
My name is Gregorio Olivas, and I'm going to be doing the credits. So Stephanie did the introduction, Conrad did the materials, me and Conrad did the procedure, Jorge and Santiago did the data analysis, Kason did the conclusion, and I did the editing and the credits.
Thank you for watching, and this concludes our lab report video.